So here we're going to solve a problem using Dalton's law of partial pressures. The setup for this says that a gaseous mixture made up of 6 grams of oxygen and 9 grams of methane is going to be placed in a 15-liter vessel at 0 degrees Celsius. Determine the partial pressure of each gas and the total pressure inside the vessel. Go ahead and pause and give that a try. Okay, so let's give it a shot. Now, the first thing we want to do is we want to convert these grams into moles. So 6.00 grams of oxygen. And we're going to have 9.00 grams of methane, CH4. Here we are. So we'll need our molar mass. For oxygen, that's going to be 1600 times 2. So that'll be 32.00. So 32.00 grams of O2 in 1 mole of O2. And we'll set up the problem and we'll grab the calculator in just a moment. Here we're going to have CH4. Carbon is 12.01 for its mass. Hydrogen is 1.008. Now we have 1 carbon, we have 3 hydrogens. Multiply that across, and of course we'll have 12.01 for carbon. Then we'll have, let's see, 3 times 8 is 24. 2, 4, a 0. There we are. And that'll be a 3. So 3.024. We do the addition-subtraction rule. So it'll be 4, 3, 0, and then 15.034. What I'm going to do is I'm going to retain that insignificant figure, and I'm just going to use the drop cap notation on that. So 15.034. 15.034 grams in 1 mole of O2. Sorry, of CH4, right? CH4 and CH4 down there as well. This is cross-canceled. That's cross-canceled. Up here we have grams cross-canceling and oxygen cross-canceling. I'll be in moles of oxygen and moles of methane. Now we're going to need the calculator. So for this first one, we'll have 6 divided by 32, and it'll be 0.1875. And then for the bottom one, it's going to be 9 divided by 15.034, and that's going to be 0.5986. So let's go ahead and just write these down right here. It'll be 0.1875 moles of O2. I've got 3 sig figs and 4 sig figs. This should only be at 3 sig figs. I'll retain the 5 to prevent round-off error, especially when it's a 5 and it could flip a coin either way, right? And we go around to the even number. I'll want to make sure that I keep it padded with an extra value to minimize my round-off errors as I go. So then I'm going to come down here, and I said it was 0.5610 moles of CH4. Now I've got the total number of moles of each. So let's find out my absolute total for these. I'm going to have, let's see, 7 plus the 1. It's going to give me an 8, and the 5, there we are. I'm going to have 8 plus 6. This is going to be 4 more. Carry 1. I'm going to have 5, 6, 7. 0.7485 moles total. Okay. So I can figure out the partial pressure for each of these gases right now. I can take the moles total and divide it underneath each of these individually. So we'll do 0.1875 for O2, and it's going to be over top of my total number of moles, 7485. So again, we'll go ahead and grab the calculator as soon as we set up both of them. For this other one, it's going to be 0.5610 divided by 0.7485. Now we grab the calculator, and we'll type in our 0.1875 divided by 0.7485. That's going to be 25%. So it'll be 0.25 for its mole. I have 3 sig figs for that. Notice that right here we'll chop it off. It is a little bit bigger than the 5, so we'll actually have to round it up. So it'll be 0.251. So 0.251 is going to be the mole fraction for O2. For this mole fraction, again, we'll grab the calculator, and we'll say it's going to be 0.5610 divided by 0.7485. And that's going to give me 0.749 other things. That's going to round that to be down, so it'll be 0.749. So 0.749 is going to be my mole fraction. Yeah, let's make it look better. Oh, that's not better. That's better. Okay. For our CH4, it's mole fraction. So here's two of our answers, our mole fractions. We've got correct sig figs, 3 sig figs and 3 sig figs. So we're set for those two. Now, for the last piece of this, what's the total pressure in the vessel? That's going to be fun for us to find out. We've got our mole fraction. We'll be able to find out the total pressure. And instead of having to solve them individually for the ideal gas law, we can actually just go ahead and use our mole fraction against the total amount of pressure. So I'm going to go ahead and erase this scratch work here as well. Okay, so let's set up our ideal gas law. We have P, V, N, R, T. Our R is going to be 0.08, let's see, 21, and that's going to be atmospheres, liters over moles Kelvin. Okay, for our temperature, we're going to be at 0 degrees Celsius. We need to convert that into Kelvin. So let's go ahead and just add the 273 to that, and that'll be 273. 273. Notice we have 0.00, so we actually get to keep our 15 in Kelvin for that one as well. So we've got this one set up. We had 0.7485 moles total. I'll write total just to remind myself this is for all of our gases and that I still have to use the partial pressures. In order to get the partial pressures, I'll use the mole fractions over here. My volume was 15 liters, 15.0 liters, and the pressure is what I'm going to determine for each of those, for the total gas and then for each of the two gases. So once again, we're ready to grab our calculator. Okay, so on this one, we're going to have PV equals nRT. Now I know it's going to be P times 15 equals N, so 0.7485, times R, 0.0821, and then times T. Remember, if you multiply by 0 right now, because you forgot to do the conversion to Kelvin, you ended up having the whole equation end up equaling 0. You have no moles of gas, you have no volume, you have destroyed Pittsburgh, as I like to say. Don't destroy Pittsburgh. Make sure you convert to Kelvin before you actually plug it in the calculator. Okay, so we're going to do our times 273.15. So this whole set of the fraction equals 16.785 some. Then we're going to divide it by the 15 as we take it back over. Remember, PV equals nRT. So we'll divide the volume over to the other side, divide by 15.0. We'll get our final answer to be 1.119. 1.119. We'll handle our sig figs. Notice that when we set up everything, we'd have 3 sig figs here, 3 sig figs, 3 sig figs. We should be at 3 sig figs as well. So our pressure should be 1.12. 0.12. Whenever we use ideal gas law, we'll still be in atmospheres. Our liters have cross-canceled, our moles have cross-canceled, our Kelvin has cross-canceled. We'll be in atmospheres. So this is going to be our total pressure. Okay, so now let's determine the partial pressures for each. So we'll have our total pressure. It's going to be 1.12 atmospheres times the partial pressure, our mole fraction, times our mole fraction. Mole fraction is 0.251, and that's going to give us our partial pressure down here. Now we're going to have the same thing set up down here. We'll take our 1.12 atmospheres times, in fact here let's just be rigorous, atmospheres and atmospheres times my 0.749 mole fraction. This is going to give me the partial pressure of each in units of atmospheres. Now notice that I didn't have a unit for my mole fraction, nor should I. They were going to cross cancel because I divided moles by moles, so the moles cross-canceled. It's just going to tell me how much of this gas I've got in total. That would be what was left, is gas divided by total, if you want to think of it that way. All right, so we can go ahead and grab our calculator again. So we'll have our 0.251 times 1.12 gives us 0.281. And then for, I'll go ahead and write it down, I guess, 0.281. And I'm just going to write it above just because I'm out of space right there. We'll grab our calculator again. So we'll have our 1.12 times 0.749, and that's going to be 0.839 atmospheres. Okay. Now the other thing we should be able to do is add them back together and get the total. So let's just try that, 0.281. And you see that we find our total atmospheric pressure to be 1.12 atmospheres of total pressure, which is what we said in the first place. It's just a way to make sure that we are being self-consistent with our answers. So you can see here we have our total pressure, our partial pressure of oxygen, our partial pressure of methane, and our total pressure in the vessel.